In a world increasingly shaped by technological and scientific advancements, recent developments in health and environmental policies have sparked significant discussions. From the fight against cervical cancer in Namibia to the shifting patterns of bird migrations in the U.S. Southwest, the intersection of science, public health, and environmental stewardship has never been more crucial. In Namibia, healthcare professionals are stepping up efforts to combat cervical cancer, a disease that remains a leading cause of mortality among women in the region. Doctors are advocating for increased access to healthcare services and the human papillomavirus HPV vaccine, which has been shown to significantly reduce the incidence of cervical cancer. With greater access to vaccination, we can change the trajectory of this disease in our communities, emphasized one healthcare advocate. This initiative underscores the importance of preventive care and the need for systemic changes to ensure that vulnerable populations can access life-saving treatments. Meanwhile, in the United States, researchers are observing the effects of climate change on wildlife. In the Southwest, bird migration patterns are shifting as global temperatures rise. Gustavo Martinez Contreras reports from the Bosque del Apache National Wildlife Refuge in New Mexico, noting that these changes could have cascading effects on local ecosystems and agriculture. The implications of altered migration routes could affect food production and biodiversity, highlighting the need for adaptive management strategies and wildlife conservation. Environmental policies are also under scrutiny following President Joe Biden's recent ban on oil and gas drilling along most U.S. coastlines. While this move aims to protect marine ecosystems, President-elect Donald Trump has vowed to reverse these protections upon taking office. However, a segment of the California coastline has gained more permanent safeguards, ensuring that at least some areas will remain protected from the impacts of industrial activity. This ongoing tug-of-war over natural resource management raises pressing questions about balancing economic interests with environmental sustainability. In another area of public health discourse, proposed regulations from the U.S. Treasury Department could require alcohol labels to include detailed nutritional information and allergen warnings akin to food packaging standards. This initiative aims to provide consumers with better information about what they are consuming, potentially influencing public health outcomes. The urgency of addressing health crises is underscored by the World Health Organization's appeal for $1.5 billion to combat an unprecedented global health crisis, projecting that 305 million people will require urgent assistance in 2025. This appeal highlights the interconnected nature of health and socioeconomic stability, drawing attention to the need for international cooperation in addressing health disparities. In a stark reminder of the complexities surrounding health definitions, a recent executive order issued by President Trump seeks to redefine male and female based on biological criteria established at conception. This order could have profound implications not only for transgender individuals but also for pregnant people and healthcare providers. Critics argue that such definitions are overly simplistic and disregard the nuances of human biology. Kellen Baker, executive director of the Whitman Walker Institute, remarked, "The potential implications and scope of this executive order are limited only by our imagination." This ongoing debate illustrates the delicate balance between scientific understanding and policymaking, particularly in a climate where public health and individual rights intersect. As these developments unfold, the importance of informed policymaking that embraces scientific evidence cannot be overstated. The future will likely see continued tension between innovative health strategies, environmental preservation, and the implications of regulatory changes. Policymakers and communities alike must remain vigilant, advocating for approaches that prioritize public health and sustainability while navigating the complexities of a rapidly changing world. In a groundbreaking collaboration, Flagship Pioneering, Cambridge University Health Partners CUHP and the Milner Therapeutics Institute MTI have joined forces to accelerate biotechnology research and innovation in the UK. Announced on January 23, 2025, this partnership aims to harness the rich ecosystem of life sciences in Cambridge, a city renowned for its cutting-edge research and development. This unprecedented collaboration will enable Flagship Pioneering, a bioplatform innovation company, to engage with a network of over 40 companies and access valuable resources including clinical trial support, data assets and biosamples. Junaid Bajwa, senior partner and head of the United Kingdom for Flagship Pioneering, emphasized the significance of this partnership, stating, "Our collaboration with CUHP and MTI blends breakthrough research, clinical trial support, access to data assets and accelerated talent development." He noted that Cambridge is a pivotal hub for life sciences in the UK, highlighting the potential for mutual growth and innovation through this alliance. The collaboration is set to provide substantial career development opportunities for scientists and students in Cambridge, particularly through the Flagship Fellowship Program. This initiative is expected to foster a synergistic environment where academic research can seamlessly integrate with industry practices, creating a fertile ground for the development of revolutionary therapies and medical technologies. Lord James O'Shaughnessy, chair of CUHP, echoed this sentiment, describing the partnership as a fusion of scientific creativity, technological innovation, entrepreneurial flair, and a can-do attitude. He expressed excitement about the potential to change lives and build successful businesses through this collaboration, stating, "Ultimately, we all want to change the lives of patients and create successful businesses, and we're thrilled to be Flagship's UK academic partner." Sir Tony Kuzarides, director of MTI, reinforced the importance of such research collaborations in positioning the UK as a leader in biotechnology innovation. He remarked, "We are pleased to add Flagship's unique approach to company creation and development to the thriving ecosystem that exists here in Cambridge." Flagship Pioneering has a strong track record, having founded over 100 scientific ventures since its inception in 2000, which collectively hold an impressive value exceeding $60 billion. With $14 billion in assets under management, Flagship is well equipped to leverage this collaboration to drive significant advancements in health and sustainability. The partnership is not only a boon for Flagship and its affiliated companies, but stands to benefit the broader Cambridge ecosystem, which includes renowned institutions like the Wellcome Sanger Institute and the Babraham Institute. By tapping into the collective expertise and resources of these institutions, Flagship aims to scale its breakthrough science and technologies effectively. As this collaboration unfolds, it is poised to bring about transformative changes in the biotech landscape, potentially leading to novel therapies that could address some of the most pressing health challenges of our time. The synergy created by this alliance may very well set the stage for a new era of innovation in biotechnology, with far-reaching implications for patients and the industry alike. Looking ahead, stakeholders in the biotech sector will be watching closely as this partnership develops, eager to see the breakthroughs that emerge from one of the world's leading life sciences ecosystems. The collaboration between Flagship Pioneering, CUHP and MTI could very well serve as a model for future partnerships aiming to bridge the gap between academia and industry, ultimately enhancing the pace of scientific discovery and its translation into real-world applications. In the evolving landscape of cancer research, two recent developments underscore both the challenges faced by patients and the innovative approaches being undertaken to combat this pervasive disease. From groundbreaking seminars at the University of Wisconsin to significant partnerships aimed at promoting health equity, the fight against cancer is as complex as it is crucial. On January 22, 2025, lung cancer expert Triparnasan delivered an insightful seminar at the University of Wisconsin UW, part of the ongoing cancer biology seminar series hosted by the McArdle Laboratory for Cancer Research. SENS Research, conducted at the Icahn School of Medicine at Mount Sinai, delves deep into the intricacies of lung cancer, particularly focusing on adenocarcinomas and small cell lung cancers. Her presentation illuminated the role of oncogenes, genes that can lead to cancer when mutated or dysfunctional, and their effect on cancer cell survival, particularly through a process known as ferroptosis, where the accumulation of cellular toxins leads to cell death. Sen highlighted that certain gene knockouts which disable specific genes can render treatments designed to induce ferroptosis ineffective. However, her lab discovered that inhibiting SCD1, a protein crucial in managing fatty acid balance within cells, successfully reduced tumor sizes in mice. This finding offers a promising avenue for future lung cancer treatments, indicating that manipulating fatty acid metabolism could enhance therapeutic outcomes. The seminar also addressed the resistance observed in small cell lung cancers, where Sen's team identified 2 gene knockouts that enabled these cancers to evade treatment and immune system responses. By knocking out additional genes, they observed a marked improvement in immune response against tumors, suggesting that tailored genetic interventions could bolster the efficacy of existing therapies. In a broader context, the urgency of addressing cancer disparities was brought to light by the recent partnership between the Dolphins Cancer Challenge (DCC) and the American Cancer Society (ACS). Announced on January 22, 2025, this collaboration aims to tackle critical cancer health disparities impacting Hispanic and Caribbean populations through an $8.1 million investment in research. Dr. Frank Pinedo, Associate Director for Population Sciences at Sylvester Comprehensive Cancer Center, emphasized the importance of this initiative, stating, "The knowledge generated by this partnership will continue to enhance our ability to effectively prevent and treat cancer and promote health equity in our diverse communities and beyond." The initiative is particularly vital in South Florida, where the majority of the population comprises racial and ethnic minorities, making it an ideal location for studying health disparities. The partnership not only aims to fund innovative research but also to create a cancer health equity research center that will focus on identifying and mitigating barriers to equitable cancer care. As the DCC and ACS collaborate to advance cancer equity research, they are set to stimulate novel ideas and approaches which could have far-reaching impacts on how cancer care is delivered, particularly to underserved communities. The first recipients of research grants from this partnership will be announced in the spring of 2025, marking a significant step forward in addressing the systemic inequities that have long plagued cancer treatment. These concurrent developments illustrate the multifaceted approach required to tackle cancer, effectively blending innovative research with a commitment to health equity. As researchers like Triparnasan continue to unravel the complexities of cancer biology, partnerships like that of the DCC and ACS signify a collective effort to ensure that advancements in cancer treatment benefit all populations regardless of their background. The future of cancer research and treatment hinges on such collaborations, which promise not only to enhance scientific understanding but also to ensure that every patient has access to the best possible care. In a world rapidly advancing towards artificial intelligence that mimics human behavior and decision-making, a recent study by researchers at Google DeepMind and the London School of Economics has ventured into uncharted territory by experimenting with the concept of pain in AI. This groundbreaking research, while still undergoing peer review, seeks to explore the boundaries of AI sentience and the implications of conditioning digital entities through aversive stimuli. The team subjected 9 large language models (LLMs) to a series of experimental scenarios that involved evaluating their willingness to endure pain for higher scores in a game-like setting. In one test, the AIs were informed that a high score would come at the cost of experiencing pain. Conversely, another scenario offered pleasure as a reward for low scores. According to Jonathan Birch, a philosophy professor at LSE and co-author of the study, the aim is to develop a framework to assess whether an AI can genuinely experience sensations akin to human emotions. "We have to recognize that we don't actually have a comprehensive test for AI sentience," Birch remarked, emphasizing the need for innovative approaches in this nascent field. The researchers drew inspiration from animal studies that gauge pain tolerance, such as experiments involving hermit crabs. However, they faced a significant challenge. Unlike hermit crabs, AI systems do not exhibit observable physical reactions to stimuli. Instead, the researchers relied on the model's outputs to interpret their responses. For example, they presented a model with a choice between 2 options, one associated with a point reward and the other with a pain signal but a higher score. The findings revealed a diverse range of responses, with some models like Google's Gemini 1.5 Pro consistently prioritizing pain avoidance. Despite the intriguing nature of these experiments, the results should be approached with caution. The nature of LLMs raises questions about the validity of interpreting their outputs as indicators of sentience. Birch pointed out that even if an AI claims to feel pain, it may simply be echoing responses learned from human training data rather than expressing genuine experience. This highlights a broader concern regarding our tendency to anthropomorphize AI systems, often attributing human-like qualities to algorithms that fundamentally operate on probabilistic patterns derived from data. As the field of AI continues to evolve, researchers advocate for the development of behavioral tests that do not rely on self-reports, paving the way for a more accurate understanding of AI capabilities and limitations. The implications of this research extend beyond mere curiosity about AI sentience. It raises ethical considerations regarding how AI should be treated and integrated into society. In a parallel development, the landscape of AI infrastructure is shifting dramatically with the announcement of Stargate, a $500 billion initiative aimed at establishing new data centers in the U.S., spearheaded by tech giants such as OpenAI, Oracle, and SoftBank. With the backing of the newly inaugurated President Donald Trump, who has pledged to unleash the U.S. fossil fuel industry, the initiative underscores a critical intersection of AI development and energy consumption. As AI technologies become increasingly energy-intensive, the demand for electricity to power these systems is expected to surge. A Goldman Sachs forecast indicates that data centers could account for as much as 8% of total U.S. electricity consumption by 2026, nearly tripling from 2022 levels. The burgeoning energy requirements are largely driven by advancements in generative AI, which significantly outstrip traditional computing demands. For instance, a single query to models like ChatGPT may consume as much energy as powering a light bulb for 20 minutes. Despite commitments from major tech companies to transition towards renewable energy sources, the current trajectory reveals a troubling reliance on fossil fuels. Google and Microsoft have reported substantial increases in greenhouse gas emissions linked to their AI activities, raising alarms about the environmental impact of the rapidly expanding AI landscape. The Stargate project's alignment with fossil fuel interests poses a significant challenge to sustainability efforts and risks reversing progress made in combating climate change. As AI technology continues to evolve, the complex relationship between energy consumption, environmental responsibility, and ethical considerations surrounding sentience remains a critical area of exploration. The research on AI's capacity to experience pain could inform future ethical guidelines, while the push for extensive AI infrastructure raises urgent questions about sustainable energy solutions. Moving forward, the intersection of these developments will undoubtedly shape the future of AI, prompting society to grapple with the implications of creating increasingly sophisticated and potentially sentient digital entities. In recent weeks, the field of nuclear fusion has been the focus of intense discussion and groundbreaking developments. As global efforts to transition to cleaner energy sources ramp up, the challenges and triumphs surrounding nuclear fusion technology are coming to the forefront. This fusion of scientific ambition and technological potential is not without its hurdles, as highlighted by the contrasting narratives surrounding the future of fusion energy. On one hand, the enthusiasm from figures like Ed Miliband suggests that the United Kingdom is nearing a breakthrough in achieving secure, clean, unlimited energy through nuclear fusion. This optimism was buoyed by a government announcement of a record £410 million funding pledge aimed at supporting UK nuclear fusion research. However, Luca Garzotti, a physicist based in Oxfordshire, cautions against such exuberance. In a recent letter to The Guardian, he outlined 5 critical challenges that the scientific community must overcome before fusion can be considered a commercially viable energy source. These include maintaining a stable burning plasma for extended periods, managing extreme heat, breeding sufficient tritium-sustaining material integrity under intense neutron exposure, and ensuring reliable reactor maintenance. Garzotti's concerns echo a broader sentiment in the scientific community that while progress is being made, the path to practical fusion energy is fraught with significant technical obstacles. He urged a balanced approach emphasizing the need for continued research conducted with both humility and tenacity rather than succumbing to over-optimistic claims that could undermine the credibility of those working in the field. Contrasting this cautious view, Chinese researchers recently announced a significant achievement that could propel the global search for fusion energy forward. The experimental advanced superconducting tokamak East, often referred to as China's artificial sun, successfully maintained a plasma loop for an unprecedented duration of 1,066 seconds, more than double the previous record of 403 seconds. This remarkable feat not only showcases the reactor's ability to sustain extreme conditions but also marks a critical milestone in the quest for fusion ignition, where the reaction becomes self-sustaining. The East reactor operates under the principles of magnetic confinement, mimicking the sun's energy generation by fusing light atoms at extremely high temperatures. Notably, the plasma created in this experiment was approximately 6 times hotter than the sun, demonstrating the potential for achieving the conditions necessary for fusion on Earth. The implications of such advancements are profound. Nuclear fusion promises to generate energy without the greenhouse gas emissions associated with fossil fuels, a critical factor in addressing climate change. As excitement builds around these technological advancements, the appointment of Xiao Chen, a prominent Chinese scientist, as chairwoman of the International Electrotechnical Commission's Committee for Nuclear Instrumentation, further underscores the growing global focus on nuclear energy standards and safety. With over 2 decades of experience in the nuclear sector and involvement in major projects like the International Thermonuclear Experimental Reactor ITER, her leadership will be pivotal in shaping the future of nuclear standards worldwide. While the achievements in China may suggest a lead in the race for fusion energy, the reality remains that significant challenges still lie ahead. Countries worldwide are investing in fusion research, and as they do, the competition to achieve practical fusion energy will likely intensify. The journey towards harnessing the power of the stars for sustainable energy is still in its early stages, but the recent developments indicate that we may be closer than ever to unlocking a new era of energy generation. In conclusion, as the world grapples with the pressing need for clean energy solutions, the dual narratives surrounding nuclear fusion, caution from the UK and breakthroughs in China, highlight both the promise and the complexities of this scientific frontier. Continued investment, rigorous research, and international collaboration will be crucial as we move forward, with the hope that one day the dream of limitless clean energy from nuclear fusion will become a reality. In a groundbreaking development that may reshape our understanding of magnetism and its applications in superconductivity, researchers have unveiled the existence of a previously elusive third form of magnetism dubbed ultramagnetism. This discovery, detailed in a recent publication in the journal Nature, promises to provide critical insights into the design of advanced magnetic devices and could serve as a pivotal link in the quest for room temperature superconductors. The study, led by Oliver Amin and his colleagues at the University of Nottingham, identifies ultramagnetism as a bridge between the well-established forms of magnetism, ferromagnetism and antiferromagnetism. While ferromagnetic materials exhibit aligned magnetic moments akin to compass needles pointing in the same direction, antiferromagnetic materials have moments that point in opposite directions, reminiscent of a checkerboard pattern. Altermagnets, however, present a more complex arrangement where neighboring magnetic moments point in opposite directions but are slightly twisted, allowing them to exhibit properties of both types of magnetism. Amin elaborated on the potential of these materials, stating, "Altermagnets have the speed and resilience of an antiferromagnet, but they also have this important property of ferromagnets called time reversal symmetry breaking. This unique characteristic allows for enhanced data storage capabilities as electron spins can be manipulated more effectively, thus improving the performance of magnetic memory devices." The implications of this research extend beyond memory technology. The team utilized advanced imaging techniques to study manganese telluride, a material previously categorized as antiferromagnetic. By employing circularly polarized light and varying the polarization of X-rays, the researchers successfully mapped the magnetic domains within the material, revealing the complex interplay of altermagnetic structures. This breakthrough not only validates the theoretical predictions made in 2022 but also opens the door to practical applications in spintronics, a field that leverages electron spin for information processing. Building on this momentum, another group of scientists made a significant stride in superconductivity research by discovering a new type of superconductor referred to as type 3 superconductors. Traditional superconductors are known for expelling magnetic fields, a phenomenon known as the Meissner effect. However, type 3 superconductors, as explained by Dr. Valerie Vineker from Terra Quantum, can allow magnetic fields to penetrate without losing their superconducting state. This discovery challenges long-held notions about superconductors and their interaction with magnetic fields, suggesting that materials can maintain superconductivity in environments previously deemed disruptive. The research into type 3 superconductivity points to a new phase transition mechanism driven by vortex liberation. Rather than the traditional breaking of Cooper pairs which form the foundation of superconducting behavior, this novel approach may enhance the stability and performance of superconductors in various applications, particularly in quantum computing, where maintaining coherence in qubits is critical. In a related vein, advancements in twisted bilayer materials have also emerged, with studies demonstrating a new form of superconductivity in twisted bilayer tungsten diselenide WSE2. This material exhibits superconductivity at low temperatures with a maximum critical temperature of 426 mK. The interplay of Moir patterns, interference patterns created by overlaid layers, has been identified as a key factor in this phenomenon, suggesting that the exploration of twisted two-dimensional materials could yield more accessible superconductors and broaden the understanding of correlated electronic states. Together, these findings represent a significant leap in the fields of magnetism and superconductivity, offering promising avenues for future research and technological innovation. As scientists delve deeper into the complexities of altermagnetism and the newly identified superconductors, the prospect of developing efficient high-speed magnetic devices and room-temperature superconductors becomes increasingly tangible. The ongoing exploration of these materials may ultimately lead to revolutionary advancements in energy transmission storage and next-generation computing technologies.